the setup. And then see. So when things are expressed like this in some kind of scientific equation, it looks a lot tougher than just the algebra. And so one of the equations is this. We let degrees Fahrenheit equal y. We let degrees Celsius equal to x. And so what we wanted is we wanted a degrees Fahrenheit temperature that was double the degrees Celsius temperature. And so this would be equation 1. Well, if degrees Fahrenheit is equal to y, we'll plug in y here. If degrees Celsius is equal to x, we'll plug in x here. So the first equation we have is y equals 2x. That's it. Now the second equation that we're going to have is just our degrees Fahrenheit is equal to 9/5 degrees C plus 32 degrees. Here. Okay, so our degrees Fahrenheit is equal to y, so we'll plug in y here. Y is equal to 9/5, and our degrees Celsius is equal to x, plus 32 degrees. So this is our second equation. So we have two equations. So what we do is we solve one of the equations for one variable. Well, this is already solved for y. And this is already solved for y. We'll just substitute that in here. So just substitute in here. And so we get 2x is equal to 9/5 x plus 32. And then we solve for x. Well, x is the Celsius temperature, right? And so that came out to 160 degrees. And this is equal to the degree C. Therefore, we plug this back in here to solve for y. And so we plug it back in here, we double that, and we get y is equal to 2x. So we get y is equal to 2x. Is equal to 2x, which is equal to 2 times 160 degrees, which is going to give us 320 degrees. And this is equal to degrees Fahrenheit. Here. And then we can double check this. And so the double check would be this. So our answers are here, 320 and 160. And so the way we can double check it is calculate one or the other. Well, it's easiest to calculate the degrees Fahrenheit. And so the degrees Fahrenheit is going to be 9/5, 160 degrees plus 32. And what does that come out to? It should come out to 320 degrees. This is the only temperature that this is valid. And so there's only, and that's it. And so these are the ways we can solve these kind of relationships. When we have two unknowns, we're going to need two equations, and we got to solve this algebraically, like this. Now, let's see how much time do I'm spending. I want to do one more, and that is with the pool water. This would be kind of a challenging problem, with two unknowns. The example was the chlorinating solution. We had an 18,000 gallon swimming pool, right? Plus, we added 0.88 liters of chlorinating solution. Well, 0.88 liters is how many gallons?
3.
Okay, so we can convert that into gallons. So 0.88 liters. We can do this using dimensional analysis with the conversion factor. 1 gallon is equivalent to 3. Anybody remember the number? 785 liters. And so how many gallons is that? Not much. Actually, I should bring my calculator.
It's 0.232.
Okay, 0.232. Is 2 rounded or not rounded?
No,
Good. Okay, so after we add the chlorinating solution, it's no longer an 18,000 gallon swimming pool. The swimming pool is going to be 18,000.232 gallons. And so it depends if it was exactly 18,000 or approximately. If this were approximately 18,000, then would 0.232 gallons make any impact on it? Not really. If this were exactly 18,000 gallons, it's no longer exactly 18,000 gallons. Now it's going to be a little bit extra, right? Now when we calculate our ppm, take a look at the setup. When we calculate our ppm was based on an 18,000 gallon, not an 18,000.232. The extra 0.232 of swimming pool, all this chlorine from the 0.232 gallons is supposed to go into the swimming pool, the 18,000 gallon swimming pool. But now all the chlorine's going into the 18,000 gallon swimming pool plus this 0.232 gallons of extra solution. And so that means our concentration of chlorine is going to be less than 1 ppm. A little bit less. Because we should add a little bit more. We should add a little bit more, not only to chlorinate the 18,000, but to leave the chlorinating solution, the 0.232 gallons worth of chlorinating solution at 1 ppm. Does that make sense? Or is this just... Does it make sense? Kinda? Okay. Let's see. What's another way of thinking about this? Another way of thinking about this is, let's say, I count the number of students in the class, right? And I have a cake. And so what I'm going to do is I'm going to divide the cake up into enough slices for everybody in the class. There are 2 ways I could divide this. I can just count this number of students and divide the cake based on the number of students, or I can count the total number of people. And if I count the total number of people, I'm missing one, me, right? And so this is what you did. You're missing one person. One person is going to be left out. Who's going to be left out? This one. The 0.232 gallons is left out because they didn't get the chlorine. Everybody else got the chlorine, the 18,000, but that 0.232 is missing that slice. Well, we can ignore the 0.232. Oh, the instructor doesn't need any cake. We can ignore that 0.232 and just say, yeah, that person's insignificant. They're small. Since they're so small, they don't really need it. We can ignore that population. But if that person's very noisy, then you're in trouble because you left that person out. This 0.232 doesn't have any chlorine. All that chlorine went into the 18,000 gallons. Does that make sense? And so now, if I really wanted to divide up the cake properly, I'd count everybody in the class, including me, not just students. Because everybody's going to be present here, and then I'm going to walk in with the cake, but I didn't come in. And so everybody's present here, the 18,000 gallons, and here comes the person with the cake. The person with the cake gives all the chlorine to the 18,000 gallons and has no chlorine left for themselves. That's how we calculated it. That's how we calculated that last problem, but and we used dimensional analysis for that. But let's compensate for it. And so the way we compensate for it is, we don't know the person coming in how big of a slice they want. Maybe they need a big slice, maybe they need a little slice. It depends on how hungry they are, right? And so we don't know how big of a slice they want, so that's one unknown. Who knows who's going to bring the cake and how much they're going to eat. But we know how many slices we have for everybody else. And so, that we need for everybody else. And so this is a 2 equation, 2 unknown type problem. And the 2 equations are going to be this. Equation 1, the total volume of pool. is going to be the 18,000 gallons already present, plus I don't know how many gallons from the chlorinating solution. You know, this is what we're supposed to find out. How much chlorinating solution are we supposed to add? So how do I know what the total volume of the pool is going to be before I even calculate it? Well, how I know is because this is a 2 equation 2 unknown problem. And so 18,000, and so this is one unknown, is V total. It's unknown. This is going to be 18,000. This is the equation for V total. The other unknown is, you know, how many X gallons of chlorinating solution I need. The X gallons of chlorinating solution will be the volume of the pool water. This is total volume of pool water. The total volume of pool water is not 18,000 gallons. The total volume is going to be a little more. And then this is in gallons. And so we go from gallons, what did we do? We went from gallons to liters of pool water. And then we went from liters of pool water to milliliters of pool water. And then we went from milliliters of pool water to grams of pool water. And then we went from grams of pool water to grams of chlorine, pure chlorine. And then we went from grams of chlorine to grams of chlorinating solution. Chlorinating solution is different. And then we went from grams of chlorinating solution to milliliters of chlorinating solution. And then we went from milliliters of chlorinating solution to liters, and we stopped there. We need to do one more step. The one more step we need to do is we need to go from liters of chlorinating solution to gallons of chlorinating solution, and then we're done. And so we're going to have the number of gallons of chlorinating solution that we have. And so this is a 2 equation 2 unknown. What's one unknown? One unknown is the total volume of pool water, because I don't know how many gallons of chlorinating solution I'm going to add to it, which is going to increase the volume of pool water. The other unknown is the gallons of chlorinating solution I'm going to add. So I need 2 equations. Well, here's my first equation. My first equation is this. And then I'm just going to substitute. And so what I'm going to do here is I'm going to get rid of V total of pool water and go 18,000 gallons plus X gallons. And so this is it. It's going to be X is equal to 18,000 plus X, parentheses, times all these conversion factors, and then to solve this one equation for X. X is going to be the gallons of chlorinating solution. The gallons of chlorinating solution are going to be a little bit more than this. It's got to be a little bit more than this, a tiny bit more than this, so that we have a little bit of chlorine left over for this 0.232. Does that make sense? And so this is a more of a challenge problem, and this is, albeit this is a tough problem, but we have others, 2 equation 2 unknown type problems that we encounter here. And so those are some of the basic types of problem solving methods that you're going to use in chemistry. All right, any questions on this? Okay, let's take a break, and then we're going to start the lab, and I'm going to go through a lab discussion first, and then we'll go do the lab next.